Hello. We've already learned that if the average binding energy per nucleon after a nuclear reaction is higher, it means that energy is released during the nuclear reaction, which is why the fission of large nuclei releases energy, and so does the fusion of small nuclei. We've always been very interested, and we're still very interested in the fusion of hydrogen. When two hydrogen 1 fuse to become a hydrogen 2, 1.44 mega electron volts of energy is released. Continuing from there, if a hydrogen 2 fused with a hydrogen 1 to form a helium 3, another 5.49 mega electron volts of energy can be harvested. And when two hydrogen 3 fuse to become a helium 4, wow, we get 12.86 mega electron volts of energy. So we are very interested in hydrogen fusion because it can solve our energy crisis problem. And not only that, the hydrogen fusion is a very clean reaction. Now compare hydrogen fusion to uranium fission. The biggest headache of uranium fission is that the fission products themselves are radioactive. Look at all these exotic elements, yeah? Rubidium lah, cesium lah, zirconium lah. They are not stable nuclei, they are radioactive. That's why the nuclear power has to be taken care of properly. We cannot just throw this into the oceans because they are going to be radioactive for hundreds of years. By the way, we have had only 2 nuclear accidents so far. In both the Chernobyl and the Fukushima, the meltdown wasn't caused by a runaway uranium fission. The cooling system for the nuclear waste broke down. It's the fission products that caused the temperature to go so high that the nuclear plants in Chernobyl and Fukushima exploded. So back to hydrogen fusion. What's the end products of hydrogen fusion? Helium. Helium is harmless. It's also not radioactive. So why are all the nuclear plants all over the world today using uranium fission instead of hydrogen fusion? Now remember, the hydrogen nucleus is positively charged. So 2 hydrogen nuclei will be repelling each other, right? So if you want to bring 2 hydrogen nuclei together to fuse, you have to do a lot of work to get them close enough. Because nuclear forces are very short range, they start to kick in only when the nuclei are like within touching distance. So a lot of work must be done if you want to move 2 nuclei to be close together so that they fuse and release energy in the process. Of course, in practice, we will not be trying to push 2 nuclei together. Instead, we just find the hydrogen gas and we try to make it hot enough. Because when it's hot enough, the hydrogen nuclei will be moving at a high velocity, right? So if they start off with high enough velocity, they may be fast enough to get so close that fusion can occur. So you start off with a very high Ke, they will trade the Ke for Ep as they come closer. So if they start off with sufficient Ke, they can come close enough for fusion to happen. So for the hydrogen nuclei to be moving at very fast speed implies the hydrogen gas is at a very, very high temperature. So how high a temperature is required? As hot as the sun, As hot as our sun. That's the kind of temperature that's required. In fact, our sun is literally a hydrogen fusion plant. That's what keeps our sun burning. In fact, our sun doesn't stop at helium. From helium, our sun will continue to fuse a few helium together to form carbon. And carbon can fuse with another helium to form oxygen. And oxygen can fuse with more helium to form silicon. Now, do you realize what I'm trying to tell you? The sun and the stars are where all the elements are produced. Our sun, just like other stars, is a chemical factory where starting from hydrogen, the nuclei are fused to form heavier and heavier elements. But it all stops when we reach the elements of iron. How come? Now remember we said iron 56 is the most stable nucleus because it has the highest binding energy per nucleon. So if you try to fuse heavier elements beyond the iron 56, you end up with lower average binding energy per nucleon, which is an energy losing business. Not only will energy not be released, energy will actually have to be absorbed for those fusion reactions to happen. Which is why you can increase the average binding energy per nucleon only up to iron. Once a star has reached iron, it has exhausted all its means of keeping itself burning using nuclear energy. And that's when the star will start to die. Now, depending on the mass of the star, different stars will die differently. If I remember correctly, our own sun, S-U-N sun, not S-O-N. So our own sun will die quietly in about 5 billion years time. Quietly as in, it will just exhaust its nuclear fuel, it will shrink, and then stop shining. But some stars, if they're big enough, they don't go away quietly. Instead of shrinking gradually, they kind of collapse very fast onto itself. So it falls so hard that it actually explodes in what is called a supernova. It's actually in this kind of supernova where all the elements beyond iron is produced. The collapse is so violent that in that split second, Everything is so energetic that those heavy elements that usually cannot be formed through the ordinary fusion process are actually formed. Do you get what I'm trying to tell you? If you look at your periodic table, all the elements beyond iron came from the explosion of a star. And in fact, all the atoms in our body must have been produced during the explosion of a star billions of years ago. So next time when you look into the beautiful night sky, do realize that you are actually much more connected to the stars than you thought. We ourselves came from the stars. We are literally stardust. Alright, that's all. Ta-ta!